On tap for today is absolute value functions and the greatest integer function. So what's an absolute value function look like? Well, basically exactly like this over here. What we're going to be doing is we're going to be graphing these things, and we'll use our calculator to help us do some of this as we move forward. But for this first one, we're just going to make a straight table like a t-chart we did back in Algebra 1. And we're going to pick some numbers like -2, -1, 0, 1, and 2, and plug them into the function. So the absolute value of -2 is 2, the absolute value of -1 is 1, 0 is 0, 1 is 1, 2 is 2. And we're going to graph those. And 0, 0 is right here, 1, 1, 2, 2, -1, 1, -2, 2. Connect the dots, it looks something like V. And all absolute value functions are going to look very similar to this. Now, we're going to look at our next example, and that's the absolute value of x plus 3. Now, the question I pose to you is, what do you think this is going to look like? What effect does this addition of 3 have on the function? Well, at this point, we're going to use our calculator to help us see what it looks like, make some kind of generalizations from all the problems we're going to be doing. So let's pop that calculator open. And to prepare ourselves to do this, we have to correct some things we did yesterday on our calculators. The first thing to do is to turn our stat plot off. So we go second, stat plot. And if your stat plot says on, you need to turn it off. So if you go down and hit number 4, it'll turn all your stat plots off. All right. The next thing we're going to do is we're going to graph this within our standard window. And the standard window is from -10 to 10. So I go to zoom, and I go down to number 6, which is standard, and it sets up a -10 to 10 XY axis for me. And now what we're going to do is we're going to plug our function into y equals. If you have anything in here, clear it out. So we're going to take and graph the absolute value of x plus 3. So to get the absolute value function, you're going to go to math, move over to number, and there's your absolute value on number 1. Select x from that, and then we're going to add 3 to that, and take and graph the function. So you notice there's our absolute value of x plus 3. Now, if I was to look at just the regular absolute value function, it would have had its vertex, if you will, down at 0, 0. So what happened? Well, the graph seemed to move up 3. So when we go back to our slide here and graph this on this particular graph, we notice that if we go, we go and pick our pen point and graph 3. And then we plug in the number 1, we get 4, 5. You'll notice that this general graph has the same exact pattern, and the key word here is pattern, as our previous y equals the absolute value of x graph. I went over 1 and up 1. I went over 2 from that vertex and up 2. Just like in our previous graph of the absolute value function that we had to start the day off. We went over 1, up 1, over 2, up 2. Well, now we've translated this graph, if you will, up 3, and then graphed the same basic absolute value graph from there. Moving on to the next graph, we have the absolute value of x minus 4. Now, you can probably guess what it's going to look like, but we'll pop it into our calculator just for kicks. So I go back to my y equals, and instead of plus 3, I'm going to take and graph minus 4. So I'll delete these. By backing up and hitting the delete button, and then subtract 4 from it. And you can pretty much guess what it's going to look like. It's going to be the same graph, but move down 4 spaces. So we come back to our table on our slide, and we move down 1, 2, 3, 4, and our graph looks very similar to what it looked before. In fact, that same pattern exists of over 1, up 1, and over 2, up 2. In our next graph, you'll notice that instead of having our constant term outside the absolute value, it's now moved inside the absolute value. Now we can plug in points, or we can again use our calculator, which I'm going to do, and go to our y equals function. And I'm going to delete a couple of these things. I'll get rid of the -4. And I'll move into here and say -2. And then I'm going to take and graph this. And again, we could have just plugged in a bunch of x and y's, but we're going to use our calculator to give us some idea of what it looks like. So you'll notice if we take now and look at the graph, its vertex has moved again, but it's moved to the right. Now, if I were to graph this, there's my vertex. If I were to pick the number 3 and plug 3 in a table, this is x and this is y, 3 gets me an output of 1. So I moved over 1 and went up 1, just like the pattern before. If I pick 4, pop it in, I get a 2 out. So again, we notice that this graph looks exactly like our first absolute value graph. It's just translated 2 units to the right. Same pattern, over 1, up 1, over 2, up 2 from our original. Okay. Now, when I'm talking about a pattern, once again, I'm talking about from this original vertex point, I go over 1 and up 1 and over 2 and up 2. The pattern is going to be key in a moment, as you'll find out. Next, we move to y equals x plus 5. Go to our calculator. What do you think is going to happen? Maybe you've already guessed, but I'm going to plug this in and show you actually what does happen. We're going to take and add 5 this time and go ahead and graph that. So notice it's an absolute value graph, but again, the vertex is translated over 5. Right now, you should start at least being able to see some patterns and some things going on. I've got -1, 2, 3. So here's where our vertex is translated. And again, if I was to pick an XY chart and just pick a couple of numbers, and I know I started at -5, if I go to -4, that's 1 away. I get 1 as my output value for y. And if I go to -3, which is actually 2 away from our vertex point, then I get a 2 out. So hey, what do you know? It's the same absolute value graph as we had before. It's just the whole thing has been translated 5 to the left. Great. Next example. So now we have f of x or y equals 1/2 times the quantity of the absolute value of x. So now we're going to take and we can actually either do this on our calculator or plug in points. Again, I think I'll do it on the calculator just to show you what's going on. Except this time, what I'm going to do is I'm going to clear everything out of here in terms of the +5. So I'll delete all that. And I'm going to call that my first graph. And that's just y equals x. And then I'm going to take and go 0.5x. I don't want to do a half. So I'll go 0.5 times the absolute value of x So what I've done is I just have now my original graph of y equals absolute value of x and a half times the absolute value of x, and we're going to kind of like compare them A, B, whatever. I graphed them. There's my first one, and there's my second one. So what's happened is the graph actually now looks a little bit different. It no longer has a pattern of over 1 and up 1 and over 2 and up 2. In fact, if we now plug this in, let's use that XY chart again. Since my vertex was still 0, 0, if I go over 1 and plug in 1, I get a half out. And over 2, I get a 1 out. So 1, a half, 2 up 1. Like so, and I can do it symmetrically on the other side as well. Here's my new graph. It appears to be a little wider. But what I want to point out is from this origin point, we notice, since these are lines at both sides, if I go up 1 and over 2, I get to another point on the graph. If I were to go up 1, and I had graphed this correctly, and over 2 again, I would have come to this point at 4, and when I plug in 4, I get out 2. So hey, look at, this is kind of like a slope. That half acts like a slope. So what have we found out? Well, I don't know yet. I'm going to guess that this 3, once again, is going to represent a slope. And this graph will look exactly like y equals x. In other words, or y equals absolute value of x. So if I plug in a 0, I get out a 0, obviously. And I'm going to pick another point of up 3 and over 1 from there. And I'm going to do it on either side because it's a V, and I'm going to go up 3 over 1 again. So notice I haven't plugged any points into my graph, but I'm claiming my graph's going to look very similar to this. And the question is, where is this point? Well, if I were to plug in a 2, that's the x value, I should get out a 6. Over here, plugging in a 2, absolute value of 2 is 2, times 3 is 6, and hey, what do you know? So I was able to actually graph that by knowing that this was my slope, and I could graph it very similarly to a line going to the right and use symmetry to graph the other half. We're getting closer and closer to this whole pattern idea tying in. Now, in fact, all absolute value graphs, f of x we know, again, is equal to y, come in this form. Y equals a times the quantity of x minus h plus k. A ends up being the slope. We already talked about that. Okay. H is a horizontal translation, which means it moves the vertex. And I could put a vertex. It moves the vertex, to the left and right. And K is a vertical translation. And again, I could say of the vertex, but in actuality, every point on the graph is actually moved, whatever the number h is and whatever the number k is. So let's take a look at a quicker way of actually going through and graphing an absolute value function using this concept. Now, here I have y equals, or f of x equals, negative 3 halves x times the quantity of x minus 6 plus 1. This 1 is going to be a vertical translation of 1 up. Now notice 6 follows the subtraction sign, and this was the absolute value of x minus h. Whoops. Of x minus h. 6 is going to move this 6 to the right. And I'm going to have a slope of negative 3 halves. So, doing all this, I move over 1, 2, 3, 4, 5, 6, and I go up 1, and I say right here, at the point 6,1 is going to be my vertex of the graph. From that vertex, if I go down 3, 1, 2, 3 over 2, I'm claiming I'm going to get another point on this graph. And if I do it on the other side symmetrically, I will get my V shape. So what I've done, without actually picking any points, just working with this pattern notation, and again, this is down 3 and over 2, I get my graph of the absolute value. Now, what is this point? That's what we want to know. Well, if I count, this was 6, 7, 8, 9 over, and 2 down. That's the point 9, negative 2. If I wanted to pick an XY chart and plug in the point 9 for X, well, then I'd have negative 3 halves times the absolute value of 9 minus 6 plus 1. Whoops. Plus 1. So 9 minus 6 is 3. And I think I got a problem because I'm not going to get 9. I counted wrong, didn't I? It's over 2, so this is actually 8. My bad. This is 8. And this is 8. Serves me right for not making my graph big enough. All right, so if I take 8 minus 6, which is 2, multiply it by negative 3 halves, I get negative 3, and add 1 to that, I get a negative 2 out. So it actually checks. Let's do another one, just to clear things up. In this case, I have a slope of 2. In the absolute value, I should have x minus h as the form. But what I have is I have x plus 3. I don't want a plus there, I want a minus. So how do I represent that as a subtraction? Well, I subtract a negative to put it in the proper form. So I want to move to the left 3 for my vertex in this case, and I want to go 4 down. So I'm going to do that, moving to the left 3, going 4 down, claiming that's my vertex. And from that vertex, I have a slope of 2. And I can do it symmetrical points on the other side. Notice I haven't plugged into this formula at all, yet I've created an accurate absolute value graph. This point right here is the point 1, 0. And I'm going to use 1, 0 in a chart just to check my answer. And if that point works, my guess is I've graphed everything else correctly. So I'm going to plug in the point 1. And I have 2 times 1 plus 3. And that's all in absolute value, minus 4. And again, I can't count right. That's a negative 1. So that's a negative 1. I get negative 1 plus 3 is 2 times 2 is 4 minus 4 is 0. So that actually checked out. Next example. We're going to look now at the greatest integer function, which is a little trickier than the absolute value function. The greatest integer function actually looks like 2 brackets. What the greatest integer function means is it talks about whatever is inside these set of brackets represents the greatest integer, not greater than the actual value inside the function. So if I graph, or let's go with a t-chart first. If I pick some numbers, Integers are always a good place to start because they're pretty easy to deal with. 3, 2, 1, 0. What is the greatest integer not greater than 3? 3. Greatest integer not greater than 2 is 2. Greatest integer not greater than 1 is 1. And the greatest integer not greater than 0 is 0. So right now I have these points. 0, 1, 1, 2, 2, 3, 3. Now, the trick comes when we start plugging in non-integer values like 2.7, 1.3, 0.26. Now, if I ask, what is the greatest integer value not greater than 2.7, that answer is 2. So at 2.7, I get a value of 2 out. What is the greatest integer of the number not greater than 1.3? That answer is 1. So at 1.3, you get 1 out. At 0.26, what is the greatest integer not greater than 0.26? Well, it's 0. Now the question is, what do I do with all these dots? I mean, how do I connect them? Well, here's what's going to happen. Any decimal value less than 1 is going to have, and actually greater than 0, any decimal value greater than 0 and less than 1 is going to have an integer value not greater than 0 for any decimal between 0 and 1. So I go from 0 all the way out till 0.9999999, which is right around here. But then at 1, I jump up to here. Since this is called a function, and we know functions have to pass a vertical line test, I can't have 2 points centered around an x value of 1. So what I have to do is at 1, 0, I'm going to create an open circle. Any decimal value between 1 and 2, 1.9, 1.8, 1.7, is going to have a greatest integer not greater than the value of the number inside of the function. It's going to have a value of 1. So I keep going once again until I get to 2. And it connects. And I keep going again from 2 to 3 until I get to 3, and I jump again. So you'll notice, and if I blow this up a little bit, here's 1, 2, 3. In between 0 and 1, not including, I have values of 0. In between 1 and 2, I have values of 1 until I get to 2. At 2, my greatest integer value is a 2. And I continue to go all the way until I get to 3. Another word for this is called a step function, because it looks like a series of steps. So my suggestion for graphing any of this stuff is to pick some integer values and then pick decimal values between those integer values to continue to learn how to graph it. Got 2 more examples for you. Greatest integer of x plus 2. Again, I'm going to pick some x and y values. I like picking 0, 1, 2, and 3. Plugging them in, I get a 2 out, 3, 4, and 5. But then I need to pick some decimal values. 0.2, 1.5, 2.7, let's say. Greatest integer of 0.2, when I plug that in, is 0 plus 2 gives me 2. Greatest integer of 1.5 is 1 plus 2. is 3. The greatest integer of 2.7 is 2 plus 2, which is 4. If I were to graph all these points, 0, 2, right here, at 1, I get 3. At 2, I get 4. And at 3, I get 5. So again, it looks like this step process is going on. At point 2, I also get 2. And I know that any decimal between there is going to give me a value of 2. So I open circle and connect the dots. In between 1 and 2, I'm going to get a value of 3 every time until I actually get to 3, in which case I get a value of 4. So again, there's my step function. A little bit harder, you have to actually plug and chug for now, because I want you to see what's going on. So that's all I've got for you today. Take a look at these questions and answer them on the form, and we'll pick up tomorrow in class.